Morning session about spectroscopies with quantum espresso. My name is Davide, and I now work at the CNR Institute, which is placed in Milan. And this is a typical windy day in Milan, and the wind is not so strong like here in Trieste. So we never have the Bora wind in Milan. So frankly, I've already realized that quantum espresso has a very much, let's say, interest into spectroscopies. That is, you don't only have you can use quantum espresso to discover new materials, to study their properties and so on, but it is also very important when you talk to experimentalists. Sometimes they ask you, can you compute or can you simulate the spectrum with different techniques that can measure? Because the idea is that, so the wish of the computational scientist is that you can establish a relation between the structure and the spectrum. And if you get the spectrum right, probably the structure is also right. This is typically the question that experimentalists ask us. It happened to me very recently that in our institute, some chemists synthesize some substituted porphyrins. And whenever they synthesize something in organic chemistry, they do NMR in order to understand the structure. They came to us, can you confirm that this is the structure that we got? And we said, no, that's not the structure. We did the calculation. The spectrum was totally different. And they decided to stop collaborating with us. OK, let's see. I have to plug this, probably. Vediamo un po' se sto coso qua va. Blum. Perfect. So I decided to divide this small lesson into two parts. And also I would like to give you an overview of the experimental technique because I think it's pretty powerful technique. And if there is already in the audience someone who is an expert of NMR, I apologize because I might oversimplify the description of the technique. And I might say also something, probably some partially incorrect things, so I apologize for that if there is already an expert on nuclear magnetic resonance. The idea is that I will do just in the first part, so an introduction from the experimental point of view, but it's an introduction which is useful also for theoreticians because I would like to, so as I said, it's a very powerful technique and you can really compute many quantities and also the interpretation of the spectra is very powerful. And then I will also do a little bit of solid-state nuclear magnetic resonance because as far as I know, Quantum Espresso is the only open source code that can compute solid-state NMR properties. Otherwise, there is in VASP, there is in CASTEP, but those are not free. And on the other hand, all the quantum chemist code, they are not periodic. So they may be free, they may be available, but they are not periodic. So maybe I'm wrong, but the Quantum Espresso is one of the fewest code that can do solid-state nuclear magnetic resonance. In the second part, I will not use the blackboard at any time. So you can see, you can take the talks. There will be a little bit of theory, but don't worry too much about that. All the slides are available, and also there are extra slides I'm not going to present, and they are there just for reference, for your reference, just in case you are interested in this. Okay, let's start with the basic principle of magnetic resonance spectroscopy. So in order to introduce the two techniques, so both techniques, so nuclear magnetic resonance and EPR, which is electron paramagnetic resonance, sometimes by the Americans is also called ESR, electron spin resonance. So it is possible to introduce the two techniques in a unified way. And the explanation is very simple. If you take a spin in your system that could be either a nuclear spin or could be the electron spin if you have a defect, a paramagnetic defect, you place it into a magnetic field, so depicted here by this magnet. Well, what happens is that the spin will experience a magnetic field which is slightly different from the external one because it will be the sum of the external and the sum of the induced field, induced by the current which are circulating into the material, and it will also experience any other kind of magnetic field generated by other magnetic moments which are present into the system. And as I said, NMR and EPR are spectroscopies. And the principle of any spectroscopy is the following. That is, when you place a spin into a magnetic field, let's suppose now for simplicity that is a spin 1/2, of course this will be split in two because of the Zeeman term. This is just the Zeeman Hamiltonian, so this will split into the energy levels of the spin. So the one upper is the one opposite to the magnetic field, the down spin is the one parallel to the magnetic field. And it's a spectroscopy in the sense that if you now send a photon, you can induce transition between the two spin states. I mean, we will see later in a few slides that the photon is actually a microwave or a radio wave. It is still a photon. And when the photon, so the incoming energy is equal to the splitting, you get absorption. So like if you were doing some optical spectroscopy, the optical spectrum gets absorption whenever you promote some transition. And here the principle is exactly the same. So basically this spectroscopy is measuring transitions between opposite spins with respect to the magnetic field. And I said, so the delta E, the splitting, is basically given by this equation, in which delta M is the change of the azimuthal, it's called azimuthal, I think it's called azimuthal quantum momentum of the spin. That's the total magnetic field, the external plus the induced and the one felt by the spin, h bar. And then there is this quantity, which is called the gyromagnetic ratio, which basically sets the energy scale of the system. Basically, the gyromagnetic ratio takes a magnetic field measured in Tesla and gives you an energy, let's say, electron volt, milli-electron volt, whatever. And it is important, so here are some useful relations of these quantities regarding the gyromagnetic ratios. So if you take a nucleus, the gyromagnetic ratio is basically proportional to the charge of the nucleus divided by the mass of the nucleus, multiplied by a small g. Small g is called the G factor, and the G factor represents the internal structure of the nucleus, so how the nucleons, so the protons and the neutrons are disposed into the nucleus, and it's a constant, it's a number. And basically the energy scale for a nuclear spin is set by the nuclear magneton. Conversely, if you have an electron, so the gyromagnetic ratio is simply the charge of the electron divided by the mass multiplied by GE. This G is the famous 2.00123, is basically 2, is the G factor of the electron, which is very famous. So it was discovered at the early birth of quantum mechanics. And the energy scale is set by the Bohr magneton. Because the mass of the nucleus is much larger than the mass of electrons, it turns out that also the Bohr magneton is also larger than the nuclear magneton. This means that in a solid, so magnetism comes only from electrons. So the magnetic moment of nuclei is order of magnitude smaller than the magnetic moment of electrons, even if they have spin 1/2, for instance, because of the mass here. And because also the nuclear magneton is basically 1,800 times smaller than the Bohr magneton. So forget about magnetism coming from nuclei. They cannot give you magnetism, the magnetism that you experience in real life. But this is very important because it sets basically the energy scale. Because if you see, so for instance, the G factor of the proton is similar to the G factor of the electron, so it's just twice as much, so it's just about the same order of magnitude. But because of the different magneton, you have that the gyromagnetic ratio of the proton is this number, whereas the one of the electron is much larger, so this is in Hertz over Tesla. This means that if I want to see a splitting, so a flipping, which is, for instance, 400 megahertz that can be measured, so 400 megahertz, I think it's in the microwave, so for the proton, I have to apply a field of 9 Tesla, about 9 Tesla. For the electron, I can apply a field which is much smaller, because luckily the magnetic moment of the electron is really larger, much larger than the one of the nucleus. And a field of 9 Tesla, I mean, it's not a piece of cake. So you need a special equipment to create such strong fields. But basically, if you put this field, you know that then the free proton will resonate, so up and down will switch at a frequency of 400 megahertz. And then you can measure changes with respect to this frequency. Why we are doing NMR on nuclei? First of all, we have to realize that not all nuclei are active, so you need to have a nuclear spin. Some nuclei, actually, they do have a spin, but maybe they are not abundant. And so doing NMR on different nuclei is always a matter of finding a good compromise. Luckily, hydrogen, which is just the proton, is a nucleus with a spin 1/2. So this is the Larmor frequency at this field, and luckily hydrogen 1 is 99% abundant. So you can do basically NMR on organic materials. And also the sensitivity is large. For instance, but if you go to deuterium first of all has a spin 1, but you see that the abundance is much smaller. And also, because of different spin, you see that there is a large difference into the Larmor frequency. So if you try to measure around 400 megahertz, you measure hydrogen. But then consider the following. In your organic material, you introduce some deuterium, and deuterium will do some ion exchange with hydrogen. You can basically switch off. You can switch off the signal of hydrogen, and the deuterium will resonate in a completely different region. So you can selectively, or you can synthesize deuterium-enriched molecules in order to switch off most of the lines of the spectra. This will simplify a lot the interpretation of the spectra. Still within the field of organic chemistry, carbon-13 is very important. It's also something which is measured very often. And carbon-13 has a spin 1/2, has a relatively low abundance, so it's only 1%, because carbon-12 is the most abundant. And carbon-12 is not NMR active, so as a spin 0, so you will not see carbon-12 into NMR. But I think I was told that it's relatively easy to do isotope enrichment also with carbon-13. And very important, I will mention also later, the nuclear spin is 1/2 for both hydrogen and carbon, and we are very lucky of that. Because as we will see later, if the nuclear spin is larger than 1/2, the nuclear is so-called quadrupolar. We will see later what does it mean. And this is very important because if it is quadrupolar, it means that the spectrum will be very broad. So the line will be broadened by the so-called quadrupolar interaction. Instead, we are lucky because the most important, let's say, element for life, they both have a spin 1/2, and so we can get very sharp lines in the spectrum. And still in the field of let's say, organic materials, sometimes now people measure nitrogen 15. Oxygen is mostly for solid-state materials. So if you want to, for instance, measure minerals, silicates, oxides, you do spectroscopy on oxygen 17. And maybe you have to also to do enrichment. But oxygen 17, you already see that it is spin 5/2, so it will give you a very large line shape. And we will see that it's important to simulate, not only to calculate the position of the transition, but also the line shape is very important. And sometimes one can do fluorine. Fluorine is a good substitute for hydrogen. And many molecules can be fluorinated. And then if you do this, so this goes in a slightly different frequency range. And okay, you have sodium, magnesium, aluminum, and silicon. Of course, then if you go to, let's say, if you think about minerals and silicates and all this kind of functional oxides, silicon is very important. 29 silicon has a spin 1/2, luckily. And these are all the others. Let me mention calcium 43. Calcium 43 has a very high nuclear spin, and so it has also a very large quadrupolar interaction. And for example, and also the abundance is very small, but people now are able to do also this kind of spectroscopy. So basically, if you know which are the elements which are present in your system, the experimentalist can really focus on every different element and extract information about the local environment of each atom, not only for hydrogen and carbon, but also for most of the others. Okay, a little bit of history of NMR. There is a long history, and the first prediction was actually by Isaac Rabi, who predicted that there should be some nuclear magnetic resonance effect in matter, and but the first experiment on a bulk sample of water was performed by Bloch and Parcel. This is a Felix Bloch, which actually is the same block of the Bloch theorem. But funny enough, he got a Nobel Prize in 1952, not for the block theorem, but for NMR. And we know that actually the block theorem is something like looks like more important to us than this kind of measurements. So basically, block and Purcell, they proved the prediction of the prediction of Rabi, and made the first measurement of the NMR of a bulk sample water. And then came 1953 Overhauser, who was also very important, who predicted the nuclear Overhauser effect, that is, you can transfer magnetization from one spin to another species. And this has become very important into analytic chemistry. And then, but the real, say, the NMR as we know today is probably, I think, is probably from the 60s, in which basically they realized that to make a good NMR spectrum, one has to use Fourier transform techniques. So it's but they are also used in other kind of spectroscopies, FT-IR, and so on. And then in 1972, there is two-dimensional NMR. I will not mention too much, but two-dimensional NMR is able to tell which atom is close to which atom. So you get a sort of two-dimensional map with correlations, and you know if atom A is close to atom B or not. It's very important. And since then, there have been many applications of NMR. And in 1985, so they were able to determine the structure of a small protein. Nowadays, it's something that people do actually. So it is possible to determine the structure of proteins, not the huge ones, let's say, medium size, totally by NMR spectroscopy without doing diffraction. Because if you have to determine the structure of a protein, you have to crystallize it. And if you are not able to crystallize it, or because it does not crystallize, there's no way you can do diffraction. So this is another important point I would like to stress. NMR is also good for disordered materials, the one that you cannot basically put in a diffractometer, where there is no periodicity. NMR can work also for disordered material, amorphous, polymers, liquids, and so on. And also, of course, crystalline solids. In 1987, there has been even the three-dimensional NMR, so you can do correlation between two atoms, and then, well, of all possible things. And then, I'm not going to mention this, but 1996, they was able to, using the residual dipolar coupling, this was even improving the solution of the structure of proteins. And now, basically, this is the technique that is being used. And this is also the list of Nobel Prizes related to NMR. I think it's complete. I don't know if in the last year there has been some other Nobel Prize. You see that we all started as a physicists, then we became chemists, and then we became medicals. I hope this is not going to happen also here. But this is also showing you that if you plan to win the Nobel Prize, probably working on NMR is a good idea. All right. And as I promised you, this is the first NMR spectrum of water. This was done actually, this is a picture of what was appearing on an oscilloscope. So the apparatus was very, was at the beginning, so doesn't say anything to you. But incredibly enough, I mean, you have the hint that there are several features in a spectrum. So this was obtained with very primitive techniques, but nevertheless, it was showing there is something here going on. And this is our, let's say, a modern, so this is still a very old spectrum of ethanol. And this is how a modern spectrum looks like. As you can see, the lines are very sharp. And each line corresponds to a different hydrogen, because ethanol has a CH3, a CH2, and OH group. And they have slightly different chemical surrounding, and so they resonate at slightly different frequencies. And it is interesting that when you do also the integrals, the integral of the spectrum, by sort of running integral, which is the red line, and the area of the peak is the number of protons. So NMR is also quantitative. So you can say, so actually this jump is 3, so it's at stage 3. This jump is 2, and this jump is 1. So here is a single proton. Here are two protons, two equivalent protons. And you can also see that these peaks are slightly splitted. This is because the nuclear spins of the two, for instance, hydrogen of the CH2 group interact among each other. And I will come back later to this. So this is how a model spectrum looks like. So notice that the lines are very sharp, and they are very reproducible, and basically one can extract all the structural information from a spectrum that looks like this. It is so precise that the chemical shifts, so these narrow lines, can be used as molecular fingerprints in chemical analysis. And I was told by a guy working in pharmaceutical that they started to using a quantum espresso and GPAF to simulate spectra, that when you make a new drug, of course, you do not patent the formula, because you don't want the other ones, the other companies to synthesize exactly the same. But you patent this, and also the structure factor of powder diffraction. So such that these are the two fingerprints. There cannot be, basically, the claim is that there are not two spectra, not two equal spectra belonging to two different molecules. Such a way you can analyze the products of your competitors, and if you find the signature of your molecule, you can sue them, and that's it. And this is the way it works, basically. And there are people, of course, in pharmaceutical companies that they take this spectrum, and like in a Sudoku game, so they try to reverse the spectrum, understand what is the structure of this molecule, and they also take the powder diffraction structural factor. They do sort of reverse Monte Carlo, and they try to understand what the molecule is. But anyway, they cannot use it. I was told that sometimes it is sufficient to synthesize the molecules and attach, let's say, a small CH3 group, or just a small variation, provided that you test it is not toxic, it's not killing your customers. You can then patent a new molecule, but of course, I mean, the working principle is already in the backbone. But this is how the pharmaceutical company work. And typical application, yeah.
What is the feeling behind each?
So is basically, if you calculate, it's not really the height, but it's the shape. If you do the integral, it's the number of protons which are exactly equivalent.
I'm talking about the mix.
Yeah.
Yes. I see that each molecule represents an atom.
Yeah. Basically, they represent one atom, or let's say two atoms which are equivalent. For instance, I think that these three CH3 are equivalent among them. Then I don't know where is the number 3 here. I can see the number 3 here, somewhere is here. But in principle, so, I mean, it's not really the height, but the shape, the integral, which gives you the number of protons. Please, I mean, interrupt me at any moment. I mean, if you have questions, curiosity before I go on. Thank you so much for the remark. And so, okay, typical applications of NMR, it's, okay, structural determination. As I told you that now one can do really proteins, but also all kind of natural products. And it is used basically also by students. I mean, in a lab, when you synthesize something, you want to understand whether your product is correct, because many organic reactions, they create a lot of products, different isomers and so on. You filtrate, separate, you do all this kind of magic, and then you go to the NMR spectrometer and you understand, okay, I'm doing the right reaction or not. And but it is also possible to study the kinetics, so reaction kinetics and so on, because we will see later another quantity important in NMR is the relaxation time. So the spins will flip and they will have some typical relaxation times. And the relaxation times depend actually on what's happening to the material. If there is some fast reaction moving, groups which are rotating and so on, they will have an impact on the relaxation time. And it is also possible to, as I said, to determine proteins, DNA, polysaccharides. It is used in drug design, and it's also used in simply in everyday life into MRI, magnetic resonance imaging. So this is, for instance, the image of the brain. Actually, the picture here, so the contrast of the picture depends on the density of water, how much water is present in the different tissues of your material. And the density of water determines the relaxation time of the proton of water, which is about 3 seconds. So if you align the proton up of the water molecule, it takes 3 seconds to flip. Which is, I mean, it's a time which is comparable to the human time. and different tissues have different density of water, and so there is a difference also in the relaxation time, and so you can do imaging, basically, with this technique. Okay. Introduction to the experimental spectra. Okay. I don't know how many of you have seen an NMR spectrometer. Question? No. I don't know if you have ever seen an NMR spectrometer. It's a big, how to say, it's a big can of metal. It's very large. Can be very large, and this is because so you have to, so in order to create such fields, such magnetic field of 14 Tesla, you must use a superconducting magnet working at the temperature of liquid helium. And so the machine is so big because there is an external cladding in which you have liquid nitrogen, which brings down the temperature. And then there is another internal circulating fluid, liquid helium. And in between, there is really when the sample is, can be put, and the machine is very large, and the sample is a few millimeters. So you have this very big stuff, and then actually you have to put in a very narrow cuvette, so which is few millimeter wide. And of course, there is a lot of electronics in the system because, and also it also costs a lot because of cooling. So you have to have a fully, so to continually replenish with liquid nitrogen and helium and so on. And the cost, probably this is underestimated, and the cost is much larger. So it can be also millions dollars. And the number that you always see on the machine is the famous megahertz of the proton. So these machines basically has a field such that the proton resonates at 600 megahertz. The larger the field, the better the spectrum. Typical machines are 400 megahertz, 600, and there are very few machines in the world that can reach up to 900 megahertz, and then the field has to be even larger than this. And 14 Tesla is not easy to reach. It's not a field that you can reach just with a magnet, with a pocket magnet. And okay, and here is how it works. So here comes the physics of nuclear magnetic resonance. So basically, the magnetic field sets the z-axis of your system. And when you have a spin, so I'm doing now a semi-classical description of it, you know that when I have a spin which is immersed in a magnetic field, what happens is that it precesses, it makes this precession movement around the z-axis, the axis of the magnetic field. Internally, the machine has basically this internal geometry. So the z-axis is where the magnetic field is, and then you have a coil, a metal coil in which you pass a current, here, and you basically inject some radio frequency into the system in order to break this symmetry. And there is another coil in which the magnetization induces a current in it. So basically, the magnetic field is here. By injecting a current in this direction, you will tilt the spin, and then this other measuring coil will, so the magnetic moment, which is rotating in this direction, will induce a current into the receiving coil, and so you can measure this signal, and then you do all this processing, signal processing, and so on. So what happens is that at a certain point, you inject a current in this coil, which creates now a magnetic field which is also in the x direction, and so z is not anymore the quantization axis. What happens is that all of a sudden your spin, it was precessing around the z-axis, now it goes down on the x plane, on the xy plane, and then you switch off this pulse, and then the z-axis goes back, it is again back the quantization axis, and we know that the spin has to go back to the initial situation equilibrium that is precessing around the z-axis. But the spin was tilted on the xy axis, and in order to go back, he has to do this sort of spiral motion. So if you plot this quantity in the xy plane, you get this curve here, which is basically a cosine multiplied by an exponential damping factor here. And if you plot the z-axis, so the z component of the spin, it is just an exponential relaxation to the maximum possible spin. The time, how is called here? The time decay. So the relaxation time of these two curves are called the T1, which is called the longitudinal spin lattice relaxation time, because it is determined mostly by the interaction with the lattice vibration, and so on. And the T2 is this called transverse spin relaxation time, and it is most determined by interaction of different spins. These two numbers, T1 and T2, can be of the order of milliseconds, seconds, and even minutes on hours. So NMR is not a fast technique like saying photoemission. So NMR is a slow technique. So you have to accumulate your spectrum for a long time. And that's not just, you don't have to measure just one of these phenomena. You have to measure hundreds of them and average over them. So making an NMR measurement can also take days for some nuclei if you want to have a very nice resolved spectrum. So it is a slow technique. So remember, the relaxation times is longer on the time scale of the molecular motion. This is very important. What's coming back? If now I concentrate on one of these curves, so this is something which is really measured from the instrument. This is the signal which is induced into the coil. This is the actual data. You can see that it's not really a cosine, but there are these wiggles here. So it is like there are several frequencies. So let me come back for a second. So here is the exponential envelope, but the cosine of omega 0. Omega 0 is the Larmor frequency of that particular nucleus. So what happens is that if you have many nuclei which experience a slightly different magnetic field, you have several different, slightly different frequencies, and basically you do the Fourier transform of this curve, and you get this. So this is why Fourier transform is important. So you simply do the signal processing and so the Fourier transform, and you immediately you basically extract all the frequencies that are present into the relaxation. So basically, the measurement is in the time domain, and then by doing the FFT, you get basically a frequency domain or sort of energy domain, and then you can plot this kind of spectra. And I mentioned about a little bit the pulses, that you apply a pulse in order to induce something to the system, to drive the system out of equilibrium and see the relaxation time. And the idea of applying just a pulse is the most simplest that people can do. Actually, the NMR machine, it's a programmable machine. That is, when you do a measurement, you have to enter a sort of program. That is, please apply a pulse for, let's say, 2 microseconds. And then apply a pulse in another direction. Then wait for 10 microseconds. Then start accumulating. So there is basically, I saw once the console, there is a small scripting language that people enter these pulse sequences. And one of the most important things for an NMR operator, the person who works, is knowing the pulse sequences. Because you can play very many games. For instance, you can excite, so you can excite at the frequency of proton, and then you send some random white noise. This way you decouple the proton from the silicon. Because otherwise, the magnetization of the two spins will sort of relax in the same way. But you can excite one, then decouple, so sending some white noise as a pulse. So in fact, basically, so it has been proposed that NMR could be a realization of quantum computing, because it is actually, it's like writing a code. So it's a program, basically, that you have to write. And you see that you do this, for instance, you do a pulse in the x direction, and then you do a pulse, then you sort of rotate the spin by 100 degrees. So I don't really know why these pulse sequences why they work, but there are libraries of pulse sequences. They are very important to measure all possible aspects of nuclear magnetic resonance. Okay, let's come to the interpretation of NMR spectra. Okay, we have seen that, okay, first of all, different isotopes have different Larmor frequencies, so they are in different parts of the electromagnetic spectrum. And this already helps us to distinguish hydrogen from carbon, from oxygen, from other. So we basically, if I can measure just one frequency window, I know that I'm only measuring just hydrogen. The resonance frequencies, which actually depends on the magnetic field experienced by the nucleus, depends on the chemical environment. Because, as I said, there are these induced currents that they change a little bit the magnetic field experienced by the nucleus. And the magnetic field, the effective magnetic field is defined by the product of the external one times 1 minus sigma, where sigma is called NMR shielding. Sigma is a small number, is of the order of ppm. So basically, the internal field differs from the external one by 10 to minus 6. Yet we can measure it. A difference in frequency of 10 to minus 6. And for technical reasons, one never works with the shielding because the machine, so also the magnetic field is not always, not every day the same. Depends also on the temperature of the machine, on the conditions of the machines, on the kind of measurements. It is better to put a reference sample in the machine and to actually measure the chemical shift, which is minus the shielding tensor of the actual sample minus the shielding of the reference sample. So basically, every morning, the NMR operator, before doing any measure, puts some standard sample in the machine, which will be shown in the next slide, measures exactly the frequency of that, and then for the rest of the day, it takes the frequency, the reference frequency, in order to compute the chemical shift. Chemical shift is meaningful. The shielding is not, from the experimental point of view, is not meaningful, because it really depends on the experimental conditions. And if you do a little bit of algebra, you discover that the chemical shift is nothing else than the Larmor frequency of the nucleus minus the one of the reference sample is relative multiplied by 10 to the 6, because it's ppm. And reference compounds, this is very important when we do calculation, because in calculation we will have to do this trick. So we also have to do this reference calculation. If you want to measure proton, the proton, the carbon, and silicon, you have to simulate a tetramethylsilane, which is a liquid. So in principle, one should also do a calculation with liquid tetramethylsilane. I think it's sufficient to do gas phase tetramethylsilane for most of the applications that we do. But for instance, if you want to do to make a reference to nitrogen 15, one should simulate a liquid ammonia. And you know that, this would imply doing Carparinello on your system, simulate liquid ammonia, and then do NMR or each snapshot and so on. But it's possible to use some secondary references in which maybe they are easier to calculate. For instance, if you do calcium, you have to simulate a calcium chloride, dichloride water solution, 1 mole per liter. I don't even remember what is a mole per liter. So it goes back really to chemistry 101. I don't really remember what it is. So I don't want to simulate calcium chloride to in aqueous solution. But I can take a different sample, maybe a solid state sample as a secondary reference. And it is just a matter of doing some sum and subtraction. We will see in the afternoon in the tutorial. And okay, the origin of the chemical shift. As I said, for NMR, it is almost entirely due by the induced currents into the system. This, for instance, if you can see the arrows here, this is the induced currents into benzene molecule when the magnetic field is perpendicular to the plane, so it is vertical here in the field. This is a very nice rendering. It looks like something from Van Gogh, right? Painting from Van Gogh. If you remember this Starry Night by Van Gogh, in which there are all these streams of painting going around. This is a very nice picture. I didn't do this. A very nice picture. And the shielding can be composed, this is just technicalities, into sort of paramagnetic contribution and diamagnetic contribution. It's not that the paramagnetic means that it is negative. So the total shielding is always positive, because it's like the Lenz's law in classical electrodynamics. When you try to induce something in a coil, the current will flow such that the induced field is opposite to the external one. So, but a system it is more paramagnetic. Let's start with diamagnetic. The diamagnetic, so a system is more diamagnetic. They say is more positive. The highest is the density of electrons, and the more let's say the system is electronegative, and the more let's say the system is spherical, and the more the currents can really flow around. Conversely, if there is some side groups which sort of hinders the rotational currents, or they make the system strongly anisotropic in shape, this gives you a shift towards smaller sigma. It's called the paramagnetic effect. Also, if you have low-lying excited states, that is, if your band gap is small, the system is more paramagnetic, which is reasonable because so in perturbation theory, so the energy gap goes to the denominator. Smaller denominator, you get a higher paramagnetic contribution. And for instance, we are doing a series of calculations on semiconductors, and we are extracting parametric and diamagnetic terms, and it is very funny that they actually depend on how much S and P character you have in your bond, because the S orbital is totally diamagnetic. The P orbital, because of these two lobes, is basically stopping the current. It's sort of blocking the current flowing around. The P orbital gives you a paramagnetic effect. And this is a way, we think that this is a way to understand how much S and P hybridization we have in a material, in a series of semiconductors. Okay, a little bit of terminology, because if you talk to experimentalists, so here is the spectrum. Notice always that the horizontal axis is opposite, so it grows in this direction. So the 0 is here, and the positive values are on the left. And if your signal is here, they say this is low field, high frequency, low shielding, more paramagnetic. Blah, blah. If it is in this direction, it is to high field with low frequency, high shielding, that is that the electrons will shield a lot the external magnetic field, and the response is very much diamagnetic. And for instance, as I was saying before, it really depends on the chemical geometry. For organic molecules, for instance, one can sort of picture how the current circulates in the various bonds, and come out with this kind of cartoons. That, for instance, if you have a double bond, so you have a region, so you have a cone in which something is more diamagnetic, and in the opposite region of space, if protons are there, they are strongly paramagnetic. And the ring effects are very important because when you have a lot of circulating currents, you have the induced field does this way. And so if you have something which is equatorial, it is the shielded, but you have something substituting which is on top of the benzene, you get a totally different shift. And as an example, so this is cyclohexane, so no conjugation. So actually this molecule is not flat, is staggered. So you see that hydrogen is what we expect from a CH2 group. It's 1.32 ppm. But if you take the corresponding aromatic system, so this carbon is in a similar situation as this one, but you see that the shift is by 7 ppm. And this is entirely due by these circulating currents that go around the system, which are very strong in this system. And it came out that if you do NMR of many substances, you can make these NMR tables, chemical shift tables. You can find them on many textbooks, chemistry, and basically they tell you, okay, if you have something which is here, maybe this is a secondary amine, or if you have something in this region, this is a alcohol, RCOOH, what is it? Carboxylic acid, I don't remember. Yeah, and so on. And the same is for carbon. So aromatic compounds are here, but you see that, for instance, let's say, if there are some chlorine substituents, you work, and here the scale is hundreds of ppm. Notice that for hydrogen the scale is a few ppms. So hydrogen has a much smaller range of chemical shifts. Carbon has something much larger. And it's very important. I mean, in calculations, basically, the agreement with experiments is a fraction of ppm for hydrogen, and maybe 1 or 2 ppm for carbon. So this is the kind of accuracy that you can reach in calculation. Otherwise, you won't be able to determine the spectrum. Okay, this is the same spectrum as before that I showed at the beginning. So the integral of the peak is the number of equivalent protons. So here is the molecule. So this proton here, the one attached to the oxygen, is unique. But instead, these two protons here attached to the carbon, they are equivalent by symmetry. And so they must have the same resonance, and they are here. And these three here, from the point of view of local symmetry, so the CH3 group, they also have the same symmetry. And of course, here at 0 is the reference, the tetramethyl-silane. And so the integral of the peak is the number of protons. The splitting of the peak is also telling you about neighboring spins, so basically the connectivity of the groups. And because, like in, let's say, magnetism, normal magnetism, there is so-called J coupling. So spins couple to this kind of term. So there is a J, a coupling constant, and the scalar product of two spins. And this exchange term falls down very rapidly in space, 1 over r cube. So you only see your neighbors. But in the spectra, you can basically see that you can basically see 4 bonds away. So it is possible to. So when you do the interpretation of spectra, this J coupling acts in space even after 4 bonds. So you can see atoms which are 4 bonds far apart, and they give you a very small splitting. I will not enter into the details of this very much. You can find them on textbooks, and unfortunately, it's not yet implemented in quantum espresso, this term, only the chemical shift. This is something that I have to do sooner or later. And the patterns also of the splitting, they follow very, very general rules like this Tartaglia triangle, so in which the ratio of the intensity follows one of these lines. And the number of lines, basically how many protons are there, and so on. Okay, so far this was the situation for let's say liquid phase NMR, one of the most common. But solid state NMR is also very important, and solid state NMR has also some interesting features. Remember that I told you that the relaxation times are very long on the time scale of the molecular motion, and so this is why the lines in liquid state NMR are very sharp. Actually, the shielding is a tensor, it's a 3x3 tensor, but what you measure in liquid is 1/3 of the trace. This is because on the time scale of the relaxation time, the molecule rotates very, very quickly. And so basically, this rotational motion averages out all the components of the chemical shift. So you don't see the tensor. You only see its trace of the tensor. But if you have a solid, which is usually, you must make it polycrystalline, so you have to powder it, and then, so with so you have to make a powder of it. What you have is that you have regions of space in which molecules have just different orientations. And here there is no averaging, because here the averaging is because of the fast motion. Here you just have, so let's say this is dynamic disorder, in a sense, dynamic averaging, and this is static averaging. And so basically these regions, they are all of them oriented differently with respect to the magnetic field. And so you don't get a sharp line, but usually you get a line which has this funny shape. This funny shape, I mean, there is an analytic formula, an analytic explanation for this shape. It also has a name, and you can extract from the first derivatives of this curve the components of the chemical shift tensor. So it is clear, because on the time scale of the relaxation times, the molecules rotate fast, but the solids don't. The solids, you just have a collection of all possible orientation, but they are fixed, they don't rotate. And this brings an additional thing, that the spectrum becomes NMR, that has become broad. And also the interaction between neighboring spins are not averaged out by the molecular motion. And this also gives you additional broadening, and also in solids the relaxation times are much longer than in liquids, and so you have to make a measurement. So your measurement can last for several hours if you do solid state NMR. And in the afternoon, if there is time left, we will try to simulate one of these funny shape of these solid state spectra. And there is also something which I like very much, that, however, as I said before, the interaction between spins is not averaged out. But if you look at the Hamiltonian of two dipoles, the magnetic dipoles moment, the Hamiltonian goes like 3 cos squared theta minus 1, so in which theta is the angle between the vector between the two centers and the magnetic field. And so the experimentalists have invented the so-called magic angle spinning. That is, instead of taking your sample vertical in the magnetic field, you can tilt by 54 degrees, in which this term goes to 0. So if you say 3 cos theta, 3 cos square theta minus 1 equals 0, it gives you theta is equal to 54. And so for doing solid state spectra, you don't put the sample vertically, but you put it tilted into the magnetic field, and you spin around this direction, and of course also in this direction. These extra spinning, they help in averaging out the broadening of the spectrum, because now it is true that the solid has many orientations with respect to the field, but the solid now is rotating. So the frame of the solid is also rotating, and so this reduces a bit the width of the spectrum. Otherwise, the NMR spectrum, without magic angle spinning, is so broad, and you cannot find anything. You cannot distinguish anything in solid state thing. It is very funny also that the speed of rotation can be of several kilohertz. So several thousands of rotations per second, which is very fast. And there is no mechanical engine, not even an electrical engine that can reach this speed and making it stable and so on. And I saw one of the samples, the cuvette in which you plate the samples. It is funny because on the glass they mount sort of the blades of a small turbine on the glass, and then they inject compressed air. The compressed air induces this very fast rotation of several kilohertz, so thousands of rotations per second. I think it's an achievement. I mean, it's and as a result, the solid-state spectra are more difficult to interpret because they also depend on this spinning speed. And as I will show you in the afternoon, it's not sufficient for us, which are theoreticians or let's say computational people, just to calculate the shift, the NMR shielding, and so on. We have also to simulate the shape of the spectrum. And this is how the spectrum looks like with no spinning, and then as you increase the spinning, you see that the lines start to become very sharp. Unfortunately, so there is no free lunch theorem, so the no free lunch theorem, you don't get just, so some of these lines are rotational sidebands, so they are generated by the rotation. And so you do the experiments at several rotation speeds, and you understand which one are the real, are the true chemical shifts, and the other are just the artifact due to the rotation of the sample. So the interpretation of solid state, first of all, you also need very sophisticated pulse sequences, and the peak assignment can be difficult, and this is why calculations are needed. Otherwise, I wouldn't be here to tell you about NMR, solid state NMR. So calculation and simulations are needed to interpret solid state NMR. Okay, this is the summary up to now. So basically, the nuclear magnetic resonance is measuring the transition between different spin states. This depends on the chemical environment because of the induced fields and so on, the splitting of the spectra. So this is the chemical shift effect, and this is the J-coupling effect. I will not talk about in these slides about multidimensional, two-dimensional NMR, because for them and for the experimental it's difficult. For us it's simple because we know for the input file which atom is connected to which. So in principle, it's straightforward to generate a two-dimensional spectrum for us. We just calculate two one-dimensional spectra, and then with a program, we just do the cross correlations between them, and this will make sort of two-dimensional peak coming out from this. And we'll also not speak about relaxation time, which to me is a fascinating topic. So how to calculate the relaxation time. It's not easy at all. Also, the theory is very complicated, but it's something that probably in future one should address. Okay, questions up to now? Let's see how much I have. Okay. You have some curiosity? Yeah?
Exactly determine the activity of an element.
Activity?
Yes. When you say some element is active,
Yeah. Okay. So if the nuclear spin is 0, there is no resonance.
Okay.
And you can look on the chemical, in the nuclear tables, there is a listing of all possible isotopes. All the G factors and nuclear are all there. So this is from the nuclear physicists, we know all of this. Typically, nuclei with even number of protons and neutrons, they have 0 spin. You mean the two-dimensional? Ah, okay. I was not planning to do that. No, basically one can, so the NMR machine, so by using a complicated pulse sequences with some delay and so on, is able to do a two-dimensional Fourier transform of the signal. By basically introducing some delays and increasing the delays, you are doing basically FFT in another direction of time. And so basically, I promise not to use the blackboard, but I'm just drawing it, drawing a schema. Basically, how the spectra are presented are this way. So this will be the shift on one side, and this, let's suppose that it is one also here. So this will be the ppm. Suppose that the spectrum is like this, and the same is like this. And what they do is that if, okay, of course, on the diagonal, these two are correlated. And so if you do a contour plot, you will get something like this. But now imagine that there is another signal here, and of course another signal here. So there will be, of course, the diagonal. But here there could be a signal or not. If there is a peak here in the two-dimensional plot, it means that this is close to this. Spatially, I mean, it means that the two protons are close in space. Otherwise, if there is no correlation here, it means that one proton is here, the other proton is there. And so basically, the two-dimensional plot, they always look like in something, lot of things on the diagonal. You might have something here, and so on. You have several contours.
On the x-axis of the distributed spectrum is in EPR, which you can use for concentration.
No, it is just multiplied 10 to the 6, because the number will be of the order to 10 to not millions, the opposite of million, micro stuff. It's related to this. There you go. So this ratio will always be of the order of magnitude 10 to minus 6. So you multiply by 10 to 6 in order to get something of the order of 1. No, it has nothing to do with concentration. Well, it is one standard exercise if you do organic chemistry. So you combine infrared and NMR spectra and so on. You know the number. I mean, you have to know that they have to tell you if it is organic or not. First of all, you count the number of protons by the area. You look at the splitting. You are immediately able to determine here is a CH3 group, here is CH2, OH, and then you took the tables, and then it's like solving the Sudoku game. You know. Only at the last moment when you put everything in place, a puzzle, you know. Only at the last moment when you put everything, so you start making hypotheses, so you start drawing your molecule. If you do this at the last moment, if everything matches the picture, that's your structure. Of course, if they tell me, if they give me, for instance, the structure of the molecule, I can put it in a computer, relax, and then they do the calculation and see whether it matches or not. Let's say for small molecules, it's a standard exercise that you do in organic chemistry courses.
I think it's quite similar question, but I think after some simulation of molecular simulation, then I predicted there is paper space in different phases, and then if I put there, I mean, is there a possible way to put there different conformations of the model in the experiment, and then, I mean, let's say here we can predict some NMR spectra and chemical shift of the each phases.
Yeah, for each conformer, yeah, for each.
Conformer, and then if I go to experiment, and then there is a way how to put the different samples of phases in the experiment.
Okay, it depends on the time scale, because the relaxation depends on the relaxation time is on the order of seconds. Depends what is the speed, what is the ratio of interconversion between the two isomers. If the barrier is small, you know that the two will interconvert faster, right? And so you have to do Boltzmann averaging on the spectra. So you have to determine the energy profile and to build a sort of Boltzmann factor, and then you calculate its configuration here, and then you can superimpose the spectra by sort of weighting them with some Boltzmann average. If instead the time for the conformity to change is longer than the relaxation time, you see the spectrum on one single, let's say, sample, one single compound.
I would decide the simple spinning frequency. Like when you apply from 0 to 2, the major field is 15. Not immediately
Sorry, the spinning speed of what?
the central spinning frequency is 9. You integrate it now.
Yes, yeah.
So it's like you from 0 to 2 to 0. And the major field is 15.
Yeah, yeah.
So how do you decide which one is right?
Well, probably we should ask experimentalists, so they have a sort of better, let's say, better way to do it. I would just scan it, but the thing, the experimentalists, they have some ideas. So I think that these are related again to the relaxation times, something that you don't know a priori. Was another question there? Probably, I have no idea, but probably weeks or months. Okay, I think we should keep up. The second part is a little bit more technical, but I will not spend much time in it because we have to end that. And now comes to the theory of NMR. I said before, what comes out from the computer are the NMR parameters. You take the NMR parameters, and then you can simulate the spectrum. And what does it mean, NMR parameters? Because when we do NMR, we assume that the Hamiltonian is the following. So this is the interaction. So the capital I is the nuclear spin, and this is the interaction with the external field, and the sigma is the shielding. So this is the Zeeman term. And this II, you see here, this is the J coupling, so the interaction between spins on different centers. They give you this kind of Hamiltonian. So this is a scalar product with a tensor in between. And if you have a nucleus which has a spin larger than 1/2, there is also coupling. So there is the so-called nuclear quadrupole effect. Okay, the chemical shift, I just repeating myself. This is the ratio between the external field and the induced one. And it can be computed by linear response theory, because formally it is derivative of the energy of the system with respect to magnetic field and a nuclear moment. And this is how Gipov does it. So Gipov does a linear response like when you do phonons. So we do linear response with respect to the magnetic field. And once we have the induced field, we just have to perform this integral, which is the Biot-Savart law. So the outcome of the calculation will be the induced current, which actually you can plot. From the induced current, we calculate the induced field, and then we evaluate, so these are here, the induced field exactly at the position of the nucleus. This can be done in reciprocal space. It's a very simple integral. And but one of the subtleties, this I would like to spend 1 minute on it, is that a magnetic field, so if you think the vector potential, so vector potential like this, 1/2 B cross R, you notice that the position operator is not compatible with periodic boundary conditions. It is the same problem of the electric polarization. So it's not well defined in periodic solids if you insist in using the position operator. Because the position operator, first of all, is not periodic and is unbound. So it goes to minus infinity in this side and goes plus infinity on the other side. So how can you put a magnetic field into a periodic system? So the trick is using a modulation. So the trick is simulating a very long wavelength magnetic field, which is half positive, half negative, so it is periodic. And basically, our sample will be placed in a small region here. So the wavelength of this magnetic field is really large. such that our simulation cell is small with respect to the wavelength, such that, so basically the magnetic field is almost constant on that scale. You can convince yourself, if you choose this to be the shape of the magnetic field, so with Q's much smaller than 1, so the wavelength, so the vector potential is like this, this you can put into linear response. It's like computing phonons as a small Q with very small wavelength. This can be easy, they can be done easy, and actually the GIP of code does this. So first you take the ground state wave function, and then you do the perturbation with respect to the vector potential, and you get the first order wave functions, and I will not write down the equations. From the first order wave function, you get the induced current, and then you, by the Biot-Savart law, you obtain the induced field. Instead, when you have a nucleus which is a spin larger than 1/2, so the nucleus is non-spherical. So it's like an egg. So it can be prolate or oblate depending on the magnitude of the spin. And the nucleus will also rotate because this will also rotate because it will couple. So a nuclear quadrupole will couple to a gradient of electric field. And if your material has a low symmetry, that is non-cubic, so the nucleus will experience a gradient of electric field. The gradient of electric field couples to the quadrupole moment and induces a rotation also of the nucleus. But this can be calculated very easily because it is just sufficient to do a self-consistent calculation and then to extract the electric field of the system and then calculate the gradients. In fact, the calculation of the chemical shifts will take a lot of time. The calculation of the EFG, electric field gradient tensor, it's immediate. So because it doesn't need any linear response, it's basically post-processing. Well, and this I leave these slides for you because this is the way the experimentalists then they use conventions for these tensors and so on. There are also several conventions to report this data, and it's always difficult to convert between one and each other. And as I said, to do the calculation with quantum express sampling waves, we do the GIPov method. This is the famous paper by Francesco Mauri in which he introduced this method. So it is based on the PAW method. I think they mentioned to you in the first days. So the PAW has the advantage that you have to do. So if you have a pseudo wave function, first of all, to calculate this quantity, you need to know the whole electron wave function, because all the wiggles of the wave function close to the nuclei are those that give you the NMR shift, basically. You need to reconstruct the wave function. So instead of having the smooth pseudo wave function, from a pseudo potential calculation, you must use actually the full all electron wave function. And in addition to this is I skipped the PAW formalism. In addition to this, in order to introduce a magnetic field into the system, it is basically you take your wave function and you do a further transformation and you multiply by a phase factor this way. Remember that if you take a particle and you move it into a magnetic field, you get a phase factor. Probably it is called the Aharonov-Bohm phase factor. And this ensures that actually your calculation is gauge invariant. It means that it does not depend on the actual choice of the vector potential. This is very important. For instance, in quantum chemistry, so all the codes based on Gaussians, they have really difficulty because when you have an incomplete basis set, your results can be gauge dependent. So it depends, for instance, on the center of the origin of the system. Luckily, the plane waves are complete enough. They are not complete formally, but they are complete enough, and we don't have gauge dependence. So it doesn't matter when we put it at 0, so the origin of our system. So the calculation will always give you the same results. And then there is also a lot of algebra going and so on, and then one gets the GIP of equations and so on. But some examples, for instance, this is a calculation by Francesco Mauri in the original paper. Here they report only the shielding, so not the chemical shift. But so the red one is the result from GIP of calculations, and the blue column are results from quantum chemistry all electron codes. As you can see, the agreement is pretty good for the light elements, whereas I don't know this is carbon. Okay, this is a little bit off, but you see also here you get a sort of a fraction of ppm for hydrogen accuracy. and here you get something like 2-3 ppm for the heavier elements. By the way, the larger the heavier the atom, the larger the shielding, because more electrons are included. So the numbers are going to grow as you go down in the periodic table. Also, notice here that there are something which is negative. So heavier elements also have a very large span of chemical shifts, and they can also be negative. Instead, you see that hydrogen is always in the same range for this kind of molecules. And this is a calculation that I did on fluorine 19 on several fluorine molecules, and comparing with the Gaussian's all-electron codes. And I had, as I said, so the completeness problem. So I had to use a cis-tuple zeta basis set, so 6 zetas for each orbital in the Gaussian calculation in order to get the same accuracy as Gipov. So because as I increase the basis set in Gaussian, I get better and better and better results. This calculation with a cis-tuple basis set took much longer than Gipov. And it just filled my hard disk with 20 gigabytes of integrals between Gaussian orbitals. So it was a nightmare. And actually, I took a table with fluorine 19, and then I thought, when I plotted, say, the experimental shift and the calculated one, of course, what I would like that they are on the diagonal. At a certain point, I had two points which I could totally switch with respect to the diagonal. So they were sort of the opposite diagonal. And then I looked back at the table. I found the original paper, and in compiling the table, they had switched 2 lines. So we were able to detect a small mistake in the paper with the table of fluorine 19. So this is also important. I mean, you can. I was also telling porphyrins. What is written on textbooks about the proton NMR of porphyrins, in my opinion, is wrong. So because we got a totally different assignment of the peaks when we did the calculation. And this is also another example of solid-state NMR. As I said, so 43 calcium is very difficult to measure because it's not abundant, and also the magnetic moment of the nucleus is small, and so this is why the spectrum is so noisy. And let's say more or less, if you use your imagination, more or less there is some matching between the calculated, and the experimental spectrum. But really you have to use some imagination. I never published these results because they are not so nice. And I would like to spend also the last, let's say, 5 or 10 minutes on electron parametric resonance, because it is really about doing both spectroscopies. So contrary to NMR, so the EPR spectrum, the EPR machine, it's much smaller. But it's probably this big like this shelf. It's really tabletop, because you don't need superconducting magnets. So the magnetic field is much smaller, and you just need electromagnets to induce to see the resonance of the electron spin. And also differently from NMR, you don't plot the spectrum, but you plot the derivative. Because when you do the derivative of a spectrum, you put in evidence all the shoulders and the minima and the tangents and so on. And this is easier to see the various components of the G tensor when you sort of do the derivative of the spectrum. And you can study paramagnetic defects in solids, radicals in proteins, and they also depends on the chemical environment because of the induced this current. Depends also on the hybridization. Similarly to NMR, these techniques are non-destructive. And you can also do experiments in vivo. So I know that you can put some also organic living material, living stuff into this thing, and then to perform the experiments. And you need actually much smaller sample in EPR and dilute spins. And this looks like some planetary model, but the interpretation of the EPR spectra is much more difficult because it's based on the spin-orbit coupling. So the first term which is generated are the orbital currents, which is this. So this is basically the coupling of the electron spin with the angular momentum. Then there is the coupling between the spin, the electron spin, and the nuclear spin, which is called hyperfine effect. And if you have multiple spins on the same nuclei, you have it's called zero field splitting. Zero field splitting is not implemented yet in Espresso, but the other two are. The zero field splitting unfortunately requires 2 electron integrals, like you do when you do exact exchange. So they're a little bit difficult to code, and they are expensive. And to interpret EPR spectra, you have to invent some spin Hamiltonians. They are very similar to the one of NMR. This looks like a sort of Zeeman. This looks like a sort of J coupling. This looks like a sort of quadrupolar interaction, but instead, so this is the zero field splitting, this is the hyperfine, and this is the Zeeman splitting. And depending on the material, depending on the spin state, and depending on how many magnetic centers you have to engineer this Hamiltonian. I mean, you have to create your own Hamiltonian, which describes your system according to the structure of your system. And then you have to start to do spin simulations for this in order to get the shape of the spectrum. To cut the story short, first of all, we need a spin orbit, but this is done in perturbation theory, because EPR is a relativistic effect. To cut the story short, okay, this we will calculate. The G tensor, similar to the shielding tensor, is formally the derivative of energy with respect to magnetic field and with respect to spin. And again, we do perturbation theory with respect to the magnetic field. And the G tensor is composed of many terms. It's not really important that you look at each of them. But the flow chart of the GIP calculation is exactly the same. So we do a ground state calculation, but this time it must be spin polarized, so n spin equal 2, because you must have a total spin. And then the system computes the response of the wave function to the magnetic field, and from phi 1, it computes the induced current that will depend on spin, and using the Biot-Savart law, is able to calculate the induced magnetic field, which depends on spin. And then if you really do the algebra, it took me a while to derive all these equations. Basically, the shift, so the change of the G tensor is just this product here, and you can compute very easily in reciprocal space. So once you have the induced current, you multiply by this is basically the electric field, gradient of potential, and multiply by spin. This is nothing else than spin orbit operator. Spin orbit operator is momentum, that is current, times spin cross electric field. And then there is also the spin other orbit, which means when the spin interacting with the orbits of other electrons. And there is no theory about that, just approximations. Something very funny I would like to point out. If I go back to the Hamiltonian, to the Pauli Hamiltonian, so of course the Pauli Hamiltonian derives, so of course Dirac Hamiltonian is the truly ab initio, in which you have all possible relativistic correction in relativistic terms. It is not easy to write a many-body Dirac equation, because the Coulomb interaction should be retarded also. It cannot be just 1 over r minus r prime. There should be relativity, so it must be covariant with respect to time and space. And there are several approximations to go from the Dirac equation, which is the perfect one, to this one. And in doing so, you get a lot of many-body terms. So whenever there is, for instance, here the spin orbit term, in principle, this is the p of one electron, and this is the s of another electron. So in principle, it's a 2-body operator. And the spin other orbit is a 3-body operator. And then if you continue, you get 4-body, 5-body operators. But in DFT, what we do is do a mean field approximation. But in principle, remember that the picture gets complicated by relativity a lot. The linear response actually doesn't work in all cases, because the linear response means that is able to only address G tensor which are close to the G factor of the free electron. The G factor of the free electron is 2.002116 something, but there are systems in which there is a strong coupling between the angular momentum and the spin system and the spin moment, that basically the linear response breaks down. And for this, we have another method which is not based on perturbation theory. I will not mention in this talk. Another important quantity is the hyperfine coupling. So that is how the electron spin couples to the nuclear spin, and this does it to the charge density, to the spin density. Sorry, and basically you have to calculate the spin density (ns) at the position of the nucleus. And so you not only have to do PAW reconstruction, but as I will show you later, also the core electrons will polarize. But when we do pseudopotentials, we assume a frozen core. The core of the potential is not polarized. And so we had to implement some extra terms and so on in order to sort of also split the the core states. The core states, they respond to the valence electrons. Otherwise, you don't get agreement with experiments. And to cut the story short, for instance, if, let's say, if your unpaired electron, like in lithium, is an s orbital, the s orbital has a density on the nucleus. It's called Fermi contact. The p and d orbitals, they have a node on the nucleus, so zero spin density on the nucleus. So if your unpaired electron is an s orbital, you can basically get it is orbital that contributes to the spin density. But if you take something like carbon, you see that the 2s orbital gives a positive response, but the 1s orbital, which is not included in the potential, which actually counteract the polarization of the 2s orbital. As a result, so the spin density on the nucleus of carbon is very small. So this is why it is very important to take into account also the relaxation of the of the very deep states. And I have implemented this, so I found a paper. I put the reference of the paper later in the slides. But this is, I warn you, this is highly experimental. So because I have to do some sort of perturbation theory, and so one never knows if this formula is complete enough to give you the correct hyperfine. I did many calculations of organic molecules, seems to work, except for a few cases in which probably better approximations are needed. And this is an example of some small radicals. So systems with ampere spins are called radicals in chemistry. For instance, this is the CH radical, and this is the hyperfine calculated without the co-relaxation and with the co-relaxation. And this is the experimental value. You can see that there is better agreement in the table, but it's even better if I plot it usually if I compare the experimental hyperfine coupling with the calculated hyperfine coupling. By the way, hyperfine coupling does not require linear response, so it is also fast, like the electric field gradient. So digitensor is slow, takes a lot of time because you have to do a linear response. Hyperfine, no, you just have to recompute the density on the nucleus, the spin density on the nucleus. And as I said before, for small organic molecules, so we go from the red points with no co-relaxation to the blue points, and so I say that to me this is a little improvement in the calculation. But then I wanted to study much let's say nastier systems that Matteo knows very well. These manganese oxide molecules. And it turns out that for some of them, when they are high spin, and here I also put Hubbard U on the manganese, so if they are high spin, you sort of get good results compared to experiments. But as the system gets more oxygens and the total spin is lower, basically it becomes so it doesn't work. But it doesn't work because the DFT doesn't work for this system. DFT is unable to describe this system. This system is spin contaminated, and we cannot describe it just with a single determinant. So this is a limitation of DFT, not a limitation of the hyperfine. But it would be nice to have a method, that is able to address also these low spin complexes because they have a multi-reference character. And to me, it's not clear how to do it. And actually, computing the spectroscopic parameter is a good test to understand if your DFT is correct, is good, is working for this kind of systems or not. And in the next slides, I put some bibliography and references for you. I'm not going to read all of them. There are some very interesting books that you can find on every, let's say, file sharing website. You don't have to buy them. And basically here you can find everything. So the full theory of spin relaxation. Actually, the spin relaxation that I showed you is semi-classical. So assume that the trajectory is semi-classical. The exact way to do is by quantum mechanics. So you have to do time propagation of the spin operator using commutators and so on. And there are programs that do it. Actually, to simulate the shape of a spectrum, you must do spin evolution sometimes. So there are programs that takes as an input the calculation from GPAV, so say from NMR, and they simulated the spectrum by simulating the spin evolution quantum mechanically, and they really simulated the experiment. And this I skip. So the EPR, the theory of EPR parameters are here, and this is the description instead of the GIP of code and of the NMR part and the co-relaxation. The converse approach I did not want to introduce, but is this approach that goes beyond the linear response and allows you to calculate things which are really in which the deviation from the G is much larger, and also to introduce relativistic effects in NMR and so on. You can use this approach. This approach is a little bit more expensive, and it's a different version of Quantum Espresso. It's not, has not been updated, but will soon port this method to the current version of GPAV. And it is based on the modern theory of orbital magnetization, which again deals with the problem of the position operator in periodic systems. And in this paper, so after a lot of algebra, we were able to derive the correct expression for the orbital magnetization for the L operator in a periodic system. And of course, there are online resources, and there are also many blogs with also data and also databases. Also, where are they? There are also databases of already measured shifts and so on. There are pseudopotentials. Many of them you can get from my website, because you need, I will show you in the afternoon, you need the special pseudopotentials to do calculations, or you can use a PAW pseudopotentials. But you cannot use ultrasoft I mean, sorry, my pseudopotentials are just the normal one with some additional part. So I also have non-conserving, ultrasoft, and PAW, but one needs some extra things in the pseudopotential file. It's called the GPAV reconstruction, and I name them dash GPAV. This you can use to calculate NMR and EPR. And I think we are close to the end. But let me acknowledge, first of all, my collaborators, those who really helped me in writing the code. And we wrote the code, I mean, not 4 hands like when you play piano, but 6 hands with Ari Seitsonen and Uwe Gertzmann. We did the first implementation of GPAV, and we were hosted by Francesco Mauri in Paris. Now he's in Rome. And you don't find a picture of him on the internet. He doesn't like to be pictured on the internet. And so we wrote the first version of GPAV, which only had the non-conserving pseudopotential support. And then a couple of years later, so Emine Kuchubenli, who was a postdoc assistant, and then a PFL, if I remember correctly, and then came back, she contributed the ultrasoft. So now you can calculate NMR spectra with ultrasoft pseudopotentials. And my friend Nicola Varini at EPFL helped me a lot on the parallelization and the optimization of the code. And several other people contributed. Most of the time, people also contributed, bug reports. It's very important for Quantum Espresso community that if you find a problem, you report it, such that we can fix it. Because we cannot do the complete testing of everything. And many of these people, they reported me some problems, and we fixed it, and we implemented new stuff, and so on. And overall, I have to thank you, all of you, for your attention. And now, with what I've told you, you will be in a position of calculate the solid-state NMR spectrum of caffeine. Okay, thank you very much.